Are you ready, kids?
Aye, Captain!
I can't hear you.
Aye, Captain!
Oh, who lives in a pineapple under the sea?
SpongeBob SquarePants!
Absorbent and yellow and porous is he.
SpongeBob SquarePants!
If nautical nonsense be something you wish,
SpongeBob SquarePants!
then drop on the deck and flop like a fish.
SpongeBob
Ready?
SquarePants!
SpongeBob SquarePants, SpongeBob SquarePants, SpongeBob SquarePants, SpongeBob SquarePants.
Ah, the sea. So fascinating, so wonderful. Here we see Bikini Bottom, teeming with life, home of one of my favorite creatures, SpongeBob SquarePants. Yes, of course he lives in a pineapple, you silly.
Why are you playing that drum? Drum? What drum? This is just my wig case. See? Come on, SpongeBob. Tackle me.
Squidward, you need bed rest. I'll keep you safe until you're well again.
Oh, I get it. You don't know what day it is, do you?
Wednesday?
Why?
National Bikini Bottom Water Appreciation Day. Does everybody know about National Bikini Bottom Water Appreciation Day? Why, sure they do. It ain't a national holiday for nothing, and I've got a couple of friends who are going to teach you fellers all about water.
Hi SpongeBob, hi Patrick, hi Sandy, I'm Ecclesia,
I'm Nicholas.
and today we are going to be talking about the different states of matter in which water can be found. The molecular structure of water is two hydrogen atoms bonded to one oxygen atom through hydrogen bonds.
Let's go into further depth on hydrogen bonds. In a polar covalent bond, the electrons shared by the atoms spend more time closer to the oxygen nucleus than the hydrogen nucleus. This is because of the electronegation difference between the hydrogen atom and the oxygen atom and the angle 105 degrees in which the bonds are arranged. The result of this pattern of unequal electron association is that the charge separation on the molecule, where one part of the molecule, oxygen, has a partial negative charge and the hydrogen atoms have a partial positive charge. Essentially, polar covalent bonds are just another way of saying hydrogen bonds.
The position in which each hydrogen is spread apart is a 105-degree angle. Water is able to exist in three of the four states of matter known as solid, liquid, and gas. In the solid phase, water is found in a hexagonal structure known as ice. The uniqueness of water is that in the solid form, ice is less dense than water is at the liquid form, which enables it to float. Observe. Okay. Ice, water, ice floating in water.
This is 0 degrees Celsius, the freezing point of water. In this state, it is a solid. Here's a solid ice at 0 degrees Celsius.
The temperature of the ice is actually increasing because the ice has begun to melt already.
Once it is melted thoroughly, it will become a liquid, and once the liquid temperature rises enough to the boiling point, 100 degrees Celsius, it will then begin to evaporate into a gas. And you can do this by heating water simply like this. We have just recently placed it on the hot plate, so it's not quite hot enough yet. I'm heating it up right now. Now, of course, it's going to take a while to heat up completely.
Later.
Here we have water that we are currently boiling on a hot plate. I'm going to place this thermometer inside to measure the temperature. If you can see, it watches the temperature rises as it's being measured. We also have water vapor coming off through the boiling water, and you can even see the bubbles towards the bottom. And as the water vapor touches the sides of the beaker, it condenses due to temperature change in small bubbles.
Let's talk about water vapor. Vapor pressure is the pressure at which water vapor is in thermodynamic equilibrium with its condensed state. At higher pressures, water will condense. The water vapor pressure is the partial pressure of water vapor in any gas mixture in equilibrium with solid or liquid water. Heat of vaporization. When water reaches its boiling point of 100 degrees Celsius, it becomes water vapor. During the heat of vaporization process, the network of hydrogen bonding present between the water molecules requires a high input of energy to transform 1 gram of liquid water into water vapor. The heat of water vaporization value is 40.65 kilojoules per mole. The amount of heat energy, 586 calories, is required to allow the water to reach its point of vaporization. Heat of fusion. The heat of fusion, otherwise known as enthalpy of fusion, of a substance is the change in energy, typically heat, to a specific quantity of the substance to change its state from a solid to a liquid at a constant pressure. Water's heat of fusion in calories is 79.72 calories per gram. Water's heat of fusion in joules is 333.55 joules per gram.
The water vapor here is coming out as a gas form, noted by the boiling point. It is the third form of water gas that is most commonly found.
12 seconds later.
Here we have the water at a rolling boil. Water has a very high specific heat capacity. Specific heat is the amount of heat needed to raise 1 gram of water by 1 degree Celsius. This is known as a calorie. The specific heat of water is 1 calorie per gram degree Celsius, which is equal to 4.186 joules per gram Celsius. Water's heat of vaporization is around 540 calories per gram at 100 degrees Celsius. And due to the vaporization, you can see the vapors here coming out of the top of the beaker.
Let's go into further detail about water. Here are some basic water facts. Water is essential to all life. All living things are composed of some percentage of water. The composition of water found in the human body ranges from 50 to 60% in the average adult. 72% of the entire earth is covered in water. 96.5% of all water can be found in Earth's oceans. The consumption of water is necessary for all plants and animals. The average human needs to drink 8 8-ounce glasses of water per day to be properly hydrated. And for all you marine creatures, if you didn't have water, well, then you'd end up like this. Now let's talk about the uniqueness of water. Water is known as the universal solvent because it dissolves more substances, otherwise known as solutes, than any other liquid on Earth. It means that wherever the water goes, whether it be through the ground or through the human body, it takes along valuable minerals, chemicals, and nutrients. The chemical composition of water and its physical attributes are what make it such an excellent solvent. Water can be used to either clean or dilute almost anything. Water is a bent, partially polar molecule, which means that it possesses the following properties. Polarity, which means that the molecule has both a positively and negatively charged end. Hydrogen bonding, which is a weak bond that is formed between the negatively charged oxygen atom of one water molecule and the positively charged hydrogen atoms of another water molecule. cohesion, which occurs because of the widespread hydrogen bonding within water, and this causes the molecules to stick to each other in a regular pattern. Surface tension is a form of cohesion, and the tension on the surface of the water occurs when the water molecules on the outside of the system align and are held together by hydrogen bonding to create a net made of atoms. And now, back to the experiments. In this experiment, we will be comparing desiccants, which is the absorption of water, and efflorescence, the loss of water, in which we can see the residue of salt and or mineral deposits. So, we're going to start off with our desiccant. And we are going to use the small little silica packet that you can find in a new box of shoes, and we are just going to add this to the water that we have in the beaker. Mix around, and we're going to set that aside. Now we are going to be looking at efflorescence. In this beaker, we have some saline solution, which we are going to place on top of this wire gauze to heat. Now, when this is heated, after all of the water has evaporated from the beaker, you should be able to see the residue that is left over at the bottom of salt. We're going to wait for a few minutes.
A few moments later.
As you can see, the water has already begun to boil and has left some residue that has formed on the inside of the beaker. This is your example of efflorescence, the loss of water, and the deposit of salt and other minerals that may have been in the water. Now we're going to look over at your desiccant again. And as you can see, inside of the beaker, the water that was once there has now been absorbed by the little silica beads. So desiccant is the absorption of water, which is the opposite of efflorescence, the loss of water. So in this experiment that we are about to conduct, we are going to be testing the electrolyte properties of these two waters. Now, for this experiment, you are going to need 2 beakers and 15 milliliters of table salt in each beaker. You have your bottled water, your tap water. This is your voltmeter. You have 3 gator clamps, a 6-volt battery, and over here, our little Christmas light. Ta-da! So for this experiment, we are going to see if this bottled water is electrolytic or non-electrolytic. So we're going to take the gator clamps and place them on the paper clips, but it does not light it up. Now, does that mean that there are no electrolytes in this water? Let us check. So you're going to take your leads and you're going to place them in evenly apart, and we're going to look at our voltmeter, and yes, we find that we do have electrolytes in the water. It is just not enough to carry a charge that will light our Christmas light. Now we will be testing the tap water to see if there are more electrolytes in here than the bottled water. As you can see, once we completed the circuit, the light bulb still did not come on. We're going to stick the leads inside of the beaker, about evenly spaced. And according to the voltmeter, the tap water actually has less voltage than the bottled water did.
Wait, what?
Notice that the label on the bottle of water that was used says that the water has been purified and enhanced with minerals for taste. So what does this mean? When salts are dissolved into water, they break apart into their component ions, creating an electrically conductive solution or an electrolyte solution. Other minerals that may stimulate electrolytes are sodium, potassium, magnesium, calcium, chloride, phosphate, and sulfate. Now we are going to add 15 milliliters of table salt into the tap water.
Go ahead and mix this in. And then we are going to add 15 milliliters more of salt into the bottled water. About. And we are going to see if now, when we complete the circuit, the Christmas bulb will light. And yay, it does. So now we are going to see if after we have added the salt to the bottled water, when we complete the circuit, if it will light up the Christmas bulb again. And it does. So, what we have found during this experiment is that if you add salt to water, it will enhance the electrolytic properties in it.
Let's take a minute to discuss the differences between electrolytes and non-electrolytes. Electrolytes versus non-electrolytes. Electrolytes can be found in a liquid or gel containing ions that can be decomposed by electrolysis that is present in a battery. Electrolytes will conduct electricity. Non-electrolytes can be found in a substance that does not readily ionize when dissolved or melted and is a poor conductor of electricity. In other words, non-electrolytes will not conduct electricity.
In this lab, we will be exploring the differences between solutions, colloids, and suspensions. So, a solution is a homogeneous mixture with two or more substances. For our solution, we will be using water and about 20 milliliters of sugar. So we're just going to pour that in. Stir it around. So, now that we have the sugar completely dissolved into the water, you have your solution. Now, in a solution, the particles of the sugar are evenly dispersed throughout and there will be no precipitate at the bottom. Another form of solution can be a sports energy drink. In this case, we have some Gatorade. So this is your solution.
Let's talk about the solution process. During the solution process, a solute particle is surrounded by the molecules of the solvent due to the strong solute-solvent attractive forces. This process is also referred to as hydration.
Now we will be taking a look at a suspension. A suspension is a heterogeneous mixture and the particles appear to be suspended throughout the solution evenly, but over a small period of time, they eventually settle at the bottom. So for our suspension, we are going to be using water and some baking soda. So we're going to pour that in. And while we mix it around, it looks as though it's being evenly dispersed and dissolving, but I have an example of previously mixed one. You will see that the baking soda has settled down at the bottom here inside of the beaker and the particles are not evenly dispersed. So this is your suspension. Finally, we will be looking at a colloid, and a colloid is a mixture that has particles dispersed throughout, but these particles are larger than simple molecules and so they're too small to settle out throughout the water. So for our colloid, we will be using milk and some water. And there you have your colloid. In this lab, we will be exploring the Tyndall effect. The Tyndall effect is also known as the scattering of light. It is used to distinguish the difference between a colloid and a solution. If you look down here, you will notice that our solution is some Gatorade. Our colloid, in this case, is water and milk. So, When a light is passed through a solution, a clear path can be seen. Taking this laser pointer, I'm going to point this through the glass, and you should be able to see the ray of light. This ray of light helps identify that this Gatorade is a true solution. Over here, we are going to do the same for our colloid, but you will notice that the particles in the colloid do not allow for a clear path, as the light beam is not allowed to pass through the colloid. The Tyndall effect is named after 19th century physicist John Tyndall. There you have the Tyndall effect. In this experiment, we are going to be testing Brownian motion. Brownian motion is the random motion of particles suspended in fluids resulting from their collision with atoms or molecules in the liquid. In this beaker, we have cool water. In this beaker, we have hot water. So, we are going to take the food coloring and we're going to place one drop into the cool water. As you can see through the beaker, the food coloring appears to be taking its time as it disperses throughout the beaker. Over here, we are going to see what happens when we add the food coloring to the warm water. As you can see, the food coloring seems to be spreading through the warm water much quicker than the cool water. And this is because the particles inside of this beaker are more excited than the ones in this beaker, and so this is helping the food coloring to spread much quicker. And this is Brownian motion.
Wait, you didn't actually think we were done, did you? Stick around. We have a bonus lab for you. Hey guys, today for this experiment, the question for the experiment is, will water fluoresce? So, we have your normal tap water, and then you have your 3 little fluorescents, and then we have some alcohol over here. All of these you can just find at Walmart for your convenience. And we are going to measure, I want to say, about 20 milliliters of water. So you take that, and you pour this inside of your test tube. And then we are going to drop some of this into here. Stir it around, and lights please. Now, if we look over here inside of the test tube, you will see the luminous at the bottom does not mix with the water. Now, why is that? It is because these two are immiscible, or another word for that is insoluble. So they won't mix. Now, lights. Okay, since we have found that the fluorescence and water are insoluble, we're going to try something different. So, because alcohol is soluble with water, we have some pre-measured alcohol in here, and we are going to dilute the fluorescence. Add some of that in there. Green, yellow, and then your pink. We are going to mix these together real quick. Okay, lights. And there you go. Okay. Now, as you can see here,
The alcohol by itself is non-fluorescent, but after we have added the fluorescence into the alcohol, it glows. So now, because we have made the fluorescence alcohol soluble, alcohol will mix with water and be soluble. So now we're going to have the tap water that has been pre-measured. And we are going to pour each one of these into a small beaker. And we are going to take our diluted solution and add it to the water. So if you mix this around a little bit, ooh, you hold these up to your black light. After adding the alcohol and the fluorescence, the water will now fluoresce. And here's your alcohol and water solution, right here in front of your black light. And this is how you can make water fluoresce at home.